I am pleased to introduce our next speaker, Eduardo Hapkost from Red Hat, who will be speaking about QEMU.
Hello? Can you hear me? So, hello, thank you for coming. My name is Eduardo. I work mostly on QEMU at the virtualization team on Red Hat, and I'm going to talk about internal abstractions and APIs inside QEMU. These are the contents of this talk. I'll first try to explain what QEMU does and has to do. I won't try to explain everything about it, but just as an introduction. Then I'll give you an overview about some of the internal APIs inside that QEMU uses to perform its job. And after that, I'll try to talk about how those abstractions work or don't work together. Now that's what's not included on this talk. I'll try to not present solutions or try to say what's the right way to do stuff. I'll just try to describe how things work. It's like more an introductory talk. Although I'll believe it can generate interesting discussions later. And also keep in mind that this is not going to cover everything, every single API inside QEMU, but just the ones that I think is most relevant. So let's see some context first. What QEMU does, what it needs to do its job. So how many of you know what QEMU is and what it does? How many of you have worked on QEMU code? Okay, that's good. So I'll try to make this part quick. So what QEMU does, it's described at its website as a generic open source machine emulator and virtualizer. And it's also a very important component when you're using KVM and Xen virtual machines. And let's see what QEMU, and QEMU has multiple interfaces to interact with the outside world. The main ones are the command line, config files. It has the human monitor protocol. That's a command line interface to control QEMU after it has started. And QMP, that's QEMU monitor protocol. That's a machine-friendly protocol to communicate with QEMU based on JSON. These are the external interface it has. And so after this very quick overview of what QEMU does from the outside, let's see what it has to do on the inside. Basically, on this slide, we see an incomplete list of what QEMU needs to handle internally. Among other things, QEMU has to keep track of configuration options, handle monitor commands, keep track of device configuration, device state, and backend configuration, and other stuff. But each of the APIs I will talk about will be used to solve one or more of those problems. Let's go inside QEMU then. After I'll try to make the introduction very quick. The first API I'll talk about is QEMU Ops. QEMU Ops is a very old node API introduced in 2009 to handle QEMU command line options and config files. It has very few basic data types, and it has basically a flat data model. QEMU Ops is basically used to parse many of the command line options inside QEMU. Or if we look at what I think is the most relevant one, it's used to handle the most of them. And also, even when a command line option is not parsed using QEMU Ops, it's used as a storage system for command line options. So we could use the same infrastructure to handle config files and command line options at the same time. So let's see how it looks like. This is one example, a simple example of QEMU Ops in action. We can see here real QEMU command line and the declarations of the code that make it possible. what's most important here is the desk session. I forgot to say, if something is unreadable here, you can see the slides on the FOSDEM website. The slides are published there. So it describes the options accepted by the dash memory option. It's very simple. The next API I'll talk about is QDev. QDev is the bus and device tree hierarchy system inside QEMU. It allows us to provide a generic interface, external and internal interface, to create, configure, and plug devices in QEMU, instead of having different APIs or different command line options to each device type. And it has a property system that allows configuration and introspection of devices. One thing that's important to keep in mind is that QDev was introduced in 2009, but when we introduced POM, that I'm going to talk about later, the QDev abstractions were basically rebuilt on top of QEMU, but I'll talk about that later. So QDev is quite successful inside QEMU. It's used internally to create and configure basically every device inside QEMU. And in addition to internal usage, it provides generic command line and monitor interface to handle devices, plug devices. And its hierarchy and property system also allows users to introspect and pick what's inside a virtual machine, for example, using the InfoQ3 device. So let's see QDev in action. QDev does lots of stuff, so I won't explain every detail here because the focus of this talk is to see how stuff works together. So this slide is just a small sample of the property system in QEMU. Oops. So we can see here how the properties of a device type like E1000 are declared inside the code. You have boilerplate code to define device types, define how they do. It's just a sample of how it is used, how things are declared in the code. The relevant parts here are so for example, the MAC option is defined inside an array. It's declared here. It has many data types and many helper macros depending on the data types of properties. This is something also provided by QDev. So QDev allows you to see the whole device tree. InfoQ3 is going to show all the buses and devices inside QEMU, and this is all handled by QDev. Next API, QAPI. So QAPI is a system for defining QEMU external interfaces. It uses a JSON-like language to define data structures and interfaces like QMP commands. That's the monitor protocol I talked about. And it provides a visitor API to implement data input, output, conversion, and so on. And it based on a QAPI schema, it generates lots of code for declaring C types corresponding to those data structures, serialization, visitors, visitor functions, QMP commands dispatching, interface introspection, and documentation. QAPI is very successfully used inside QEMU to define and dispatch all QMP commands and to define and parse a few command line options. So every single data structure used in QMP is heavily documented on the QAPI schema. So it's a great system, and we have been trying to use QAPI more inside QEMU when defining external interfaces. So let's see QAPI in action. This is a QMP command that's sharedev add. It has a few arguments. One argument is ID and another one is backend. These are the actual QMP messages being exchanged. the response is empty because there are no extra data being returned. And this is how it's described on the QAPI schema. Basically, I removed all the documentation comments, but basically, data structures are all-defined. You have declarations to declare how QMP comments look like, what they get in an argument, what they return. You can, this comment maybe uses a feature that's called a union, so you can have different attributes depending on the type of option you are using. And this is the function that's going to implement the comment. So the QAPI system is going to take care of serializing everything, calling the right function using a simple C struct, and then returning the data later. So last but not least, we have QEMU. QEMU is the QEMU object model. Don't confuse that with QObject. That's something else I'm not going to cover in this talk. So QEMU started as a generalization of QDev. It has lots of interesting features. I won't try to explain everything about it. It would cover a whole talk. So basically, it has a type hierarchy of classes. It has a property system, and basically all the abstractions in QDev were rebuilt on top of QEMU. So many of the QDev codes are just wrappers around QEMU. And let's see QEMU in action. These are just a few examples. So I won't try to explain how QEMU works inside, but I just see where it is used. It's used when you're using QDev. When you are plugging a device, QDev is built on top of QEMU. It's used when you are creating a backend object file, backend object. It can represent some entity that's used to implement a VM. It's used by the machine type system in QEMU. It's used by the accelerator system. It's used by the CPU model configuration system. And it is also used internally. For example, we have data types for IRQs, memory regions. So it's used at lots of places. We benefit from the property system when we are dealing with options on the command line, when we are dealing with CPU options or QDev options. And clearly we have lots of other places where QEMU is used that I'm not even aware of. So it is everywhere. And I see that. Now that we have seen an introduction to each of those abstractions individually, let's see how they work together. That's where things get interesting. First example we have inside QEMU is the -NUMA command line option. It's one case where we mix QEMU ops and QAPI together. Let's see how it does that. This is how the -NUMA command line option is defined on the code. Note the empty desk field here. That's where the accepted options for -NUMA would be defined, and it's simply empty. Instead of defining the options here, you use the QAPI schema to define that. So all the options on -NUMA, let's go back here. These options here are defined on the QAPI schema. So basically you have a declaration saying that structure name and NUMA node options can have those fields, and those fields can be specified on the command line. And we have some glue code to convert the QEMU ops data to QAPI data, so they can be used elsewhere on the code. That's used by this trick here. So we have the visitor API for provided by QAPI, and it can be used to convert QEMU options to QAPI data structures and validate them. So let's summarize this case. NUMA is fortunately on one case where things are working as they should, because all the options are specified on the QAPI schema, and there's no duplication. There's no options declared on the QEMU ops declarations and the QAPI schema. And this is made possible by the ops visitor helper. Other command line options that are very similar are -net, -net-dev, -CPI table, and -machine. So this is basically an example where things are working. We can make sure that QEMOps and QAPI work together. Let's see another example. Let's see one case where QAPI and QOM are used together. This is the object add QMP command. It's used to create a backend object, basically. It's a generic system to create objects inside QEMU. And there is a QMP command to do that. It has to take a few arguments. It takes the type of the object and the additional properties for the object. And the properties accepted by object add are defined basically by the object itself, the object class itself. So the file name arguments seen on the comment here are declared not on the KPI schema, but declared at the QOM code by the RNG random class, because we are using the QOM property system to declare which properties the backend object accepts. And the QAPI schema looks like this. So we have a command called object add. It has those two arguments, and also an additional argument that can take any data type. So basically it means that the QAPI schema says you can put anything here. What happens here? So in case of object add, the QAPI schema is incomplete. You don't have the QOM data appearing on the QAPI schema, so you don't benefit from it. You don't have the type checks provided by QAPI. You don't have the generated code that you could use to implement the interface. And we have a very similar problem with device add. It's even a bit more complex on device add because of the way the properties are defined on the schema, but I won't get into that. So in this case, the abstractions don't work perfectly together. We have some limitations here. Let's see another example that's based on QOM. That's -CPU. So the CPU model system inside QEMU uses QOM internally, because basically CPUs are devices, devices are QDEV devices, and QDEV is implemented using QOM. And we have command line options that are going to control the CPU devices, basically. So let's see how it works. This is an example of the options accepted by -CPU, or how they are specified. In the case of CPUs, each architecture registers their own QOM properties the way they need. So in the case of x86, we have a few static properties using the QDEV property system, and we also have some properties declared registered at runtime, because we have lots of CPU features configured by, at least on x86. I don't know about the details on other architectures. And this is the glue code we have. The glue code is going to take the command line options. It's not using QEMU ops, it's using its own parser, but that's something we want to change. And using the QDEV global property system, that's something provided by QDEV that ensures that every device of a given type is going to have a key property set. So basically, when you use -CPU, the CPU features declared on the command line are going to be declared as QDev options. So the summary for -CPU is, we don't even have a QAPI schema for -CPU. It's simply not very well documented. So you don't have any information required to know which command line options are supported by -CPU. If you want to know that, there's no interface to do that. And it has an additional problem that it does not even use QEMU ops to do that, but that's something, as I said, that we need to change. So this is one example where we see the friction between those interfaces. The Chrome-based stuff being used from the command line is not very well integrated. Let's see another example, even more complex, related to CPU options. That's query CPU model extension, QMP command. So this is one case where we have a Chrome-based implementation and a QAPI-based interface. I won't try to explain what the command does here, but basically you get a CPU model name and you are going to get information about it on the props attribute, about all the features inside the CPU, all the properties for a CPU model. And this is the QAPI schema for that command. Like on the object add case, we have to use this hack here that basically says the props field can have anything. So the semantics of this props field is documented on the documentation for the command, but the schema doesn't tell us which properties can be there, what's the data type, what you can expect there. You need to read the documentation to do that. So, summarizing this case, in the case of query CPU model expansion, the QAPI schema is also incomplete. It doesn't have all the information we want. And it has an additional problem that the glue code that will make sure the Chrome implementation can report QAPI-based data is specific for each architecture of CPUs. So we need to clean up that to make sure we use common code to see how we can get common infrastructure to that. There's a pattern here that can be summarized here, is that when you're using Chrome, you normally have trouble when using something QAPI-based, because Chrome classes and properties are registered at runtime, especially Chrome properties. They are not a static file in the code. They are added at runtime when you're initializing QEMU. But the QAPI schema is a static file. So you simply can't represent any runtime information on the QAPI schema. So that's why we have these issues with Chrome being used with QAPI. So I think I was faster than I expected. So, concluding that, my first recommendation here is that lots of practices inside QEMU are not documented anywhere, or not very well documented. So this talk is an attempt to write down some of the stuff that we have learned in practice, but if you have any question, don't hesitate to ask on the QEMU Devel mailing list. Because sometimes we are still discovering where we want to go, what the practice we want to follow. So it's good to have these things explicitly discussed on the mailing list. I think I'll try to just to show a summary, as we have a few times, of the okay. So this is something I had as bonus material if we had time. Just to summarize how the data types represented on each API looks like. So most of the APIs, or all of them, involve some kind of data representation. And another issue we have is that they don't support the same data model. Pure API is the most complete one. It supports all the range of data types I enumerated here, but QEMU Ops and QDev are more limited. QOM is also a bit more limited, but it has some limited support to more complex types. So this is one source of the friction we have when we are trying to make one abstraction talk to another one. Now, something else I tried to summarize. Okay, this is very hard to read, but basically, on all those abstractions here, we have some equivalent data structures. We have often some type or option type, some option type defined. We normally have a property system say which attributes can be set for each option type, device type, or schema data structure. On most of these cases, we can have mechanisms to define defaults for them. And then we have the runtime data structures that are basically the options themselves, the devices themselves, or the actual C-strut runtime data. And one difference in this case that makes it difficult that I tried to explain before is that some of the data that is static, for example for QAPI, or that is static for QDev, is actually not static for the other systems. So QOM properties can be registered at runtime, and you can easily translate to the static data on QDev. The defaults for QEMU Ops and QOM are also defined at runtime, so you can't just convert to the other data structures later. So this is another source of friction. So, questions? Comments? Yep. Well, you can ask and I can repeat.
Yeah, I just wanted to ask, is there any plan or any effort to reduce...
Thank you very much. Okay, so Eduardo, is there any plan to get rid of some of these layers, to do something about all this? Because there's a lot of duplication, and it's also causing bugs, and it's an effort, like it causes a lot of effort during development. You don't know what you should do. Sometimes the overlap causes problems as well.
Yeah, that's a good question, because the difficult part of this question one is that sometimes we are not sure, or we are not on agreement of where to go. But I can say what I know, or my impressions. My impressions are that instead of removing those layers, we can try to make them thinner. For example, QEMU Ops today have a way to define those options, and we have a way to define command line options using QOM or QAPI. If we could move all the command line options to be defined using QAPI or QOM, then we could remove the option definitions from QEMU Ops and have only parser. On the other case of QAPI and QOM, I think they are going to live, and we just need to make them work together. I think we won't get rid of QOM, or we won't get rid of the runtime registration of properties, so we just need to make sure they work together. There is some work to describe command line options in QAPI, in a language like the QAPI schema, but I don't know the details of how it's going to be done, but we are trying to do that. So I don't think, on the case of the abstractions I showed, I don't think any of them is going to be removed in the near term, but we can make them be rebuilt on top of the others and make some of the code inside them less necessary. QDev is one example. So QDev was was basically rebuilt on top of QEMU, but it still has some abstractions that are not inside QEMU, but we can work to make QDev reuse QEMU code instead of duplicating. So I don't think we can remove the layers, but we can reduce duplication between them by reusing the same infrastructure. One example are the parsers. When looking at the code for the talk, I found out that we have at least three different parsers for integer numbers, for strings. So you have a number on the string, you need to parse it. There are three different implementations, each one with different bugs and with different limitations. So I think we can reduce duplication not by removing layers, because it's going to be a huge effort, but by making them benefit from each other and reusing code from each other. Anybody else? So thank you. Okay. Yeah.
Do you have any recommendations on how other projects could avoid this mess, basically, on the long term?
Sorry, I couldn't hear everything.
You've got multiple APIs with overlapping functionality and whatnot. Do you have any insight for other developers working on other projects on how to avoid ending up with that?
Yeah, I don't have any advice, but I can say what I think went wrong. For example, I think some of the new abstractions were added without a clear plan to replace other ones. So when we introduced QEMU and tried to convert all the existing devices to use QEMU or QDev, there was no clear plan to say, okay, we are going to convert these devices and then these ones, and we are going to keep this and this abstraction and remove that one. There was no clear plan to do that. When we started using QEMU API for some of the command line options, there was no clear plan to say, okay, this is the process we are going to follow. We want to convert the old ones to the new API. So I think that's what didn't work on QEMU. There was no clear plan. Yes?
Adding another answer is having test cases ready from the start makes any conversions absolutely easy. That was one of the issues that we were facing.
Anybody else? Okay, thank you. So the slides are available there, and if you don't want to write down the link, you can just get the slides and follow them. There's a blog post I wrote about with an introduction to QEMU APIs with links to other ones. And I have been trying to write a summary of each one, so if you want to follow it. Thank you very much.